Hello, my name is Nigel Arnell and I'm from the Department of Meteorology at the University of Reading. I'd like to talk today about linking climate to hazards and risks. I'll look specifically at what we know and will highlight some key gaps and opportunities. I will start with providing a short conceptual overview of the relationship between climate hazards and risks. The conceptual framing I'll discuss is a very powerful way of helping us understand how risks will change in the future and how we can estimate changes in risk. I then want to talk a bit about a global perspective and what it implies for risks to the UK, before looking at some new projections of changes in risk in the UK. The first part of the conceptual framing recognises that there is a cascade of risks, from relatively straightforward direct consequences of climate change at the top, such as impacts on crop growth, through second-order impacts to larger systemic risks. I've used hunger and food security as an example of a systemic risk here, but another example would be wholesale and linked failure of power and communication systems. The main point is that the factors which affect these risks vary through the cascade. The closer we get to systemic risks, which are arguably the most worrying, the further we move away from direct climate drivers of risk. The contribution of these different drivers of risk is shown in this diagram, drawn from the disaster risk reduction community and widely publicised through the IPCC Special Report on Extremes from 2012. It conceptualises risk as a function of hazard, the physical environment, exposure, the people and assets in the way of damaging events, and vulnerability, or the propensity to suffer harm. Climate change alters the physical component, whilst socio-economic change alters exposure and vulnerability. Climate change is, of course, driven by socio-economic change, but when we are thinking about impacts and risks, we can, for practical purposes, treat them as independent. Exposure can be expressed in quantitative terms, but vulnerability is a more qualitative characteristic of a system. It reflects factors such as governance, access to wealth and power, and institutional arrangements. These different drivers are subject to different types of uncertainty. How climate changes depends on the rate of forcing and how the climate system responds to increasing greenhouse gas concentrations. How exposure changes depends on, for example, population change and movement to or away from hazardous locations. How vulnerability changes depends on changes in institutions and governance. The response to the climate system to a given level of forcing is characterised by scientific uncertainty, our understanding of how the climate system works and ability to model consequences. We typically represent this by an ensemble of climate models. At the other extreme, the future evolution of governance and institutions is subject to radical uncertainty. We do not know what they will be in the future, and we cannot know. We have to describe plausible futures through narratives or stories. Between the two is what I've called conditionally rational. We don't know the precise drivers of future emissions or population growth, but we can make some assumptions, some quantitative assessments based on underlying narratives. We can make an assumption about future economic systems and the use of fossil fuels, for example, and convert these into emissions scenarios to run climate models. The key point here is that we can express some drivers quantitatively and perhaps probabilistically, but others have to be expressed as plausible stories. We cannot assign likelihoods to these stories. I'll illustrate these points from a global perspective. I've plotted here 5 indicators of change in future climate hazard, and these plots show the global average. The details are not important, but the plots show that at the global scale, hazards from drought, flood, heatwave and crop failure increase, but at different rates through the century. The different colours represent different narratives or stories about future emissions. In practice here, blue is RCP 2.6 and red is RCP 8.5, whilst the shaded areas show the scientific uncertainty in projected changes. There is a big difference between the different stories, and for a given story, though the direction of change is clear, the magnitude of change is uncertain. The previous slide showed change in climate hazard. These changes are combined with changes in exposure to define impact. We can't know how exposure will change, so we represent plausible changes by a series of stories. Here we see 5 different socio-economic scenarios. The plots show numbers of people exposed to different hazards, or the area of cropland. In each case, the different colours represent different rates of emissions, from low to high. For 3 of the indicators, the 5 socio-economic scenarios are shown as the 5 separate bars. The height of the bars represents scientific uncertainty. So we've combined radical and scientific uncertainty in the same plot. Again, the details are not too important, but the plots tell us that the numbers of people affected by climate change depend partly on the rate of climate change, the different colours, and partly on our socio-economic assumptions, the different bars. In practice, the effects of climate change for a given forcing and socio-economic scenario vary across space, and this is illustrated here for one particular plausible climate model pattern. We use the pattern from climate models because they maintain realistic physical representations and relationships between different places. So what are the implications for risks to the UK? Overall, the evidence is that hazard and risks will increase at the global scale, but with variations from region to region. The first key implication is that the precise consequences for the UK depend on the spatial pattern of change, which parts of the world are most affected, relative to the parts of the world that are directly relevant, in whatever way, economically or politically, to the UK. In order to estimate these risks, we therefore need to have a robust idea of how changing greenhouse gas emissions affect weather and climate in different regions. And this is why climate models are particularly important. They are used to project changes in particular regions. The second point is that the international dimension primarily affects the UK through the large-scale systemic risks, such as insecurity, displacement, and supply chain shocks. The direct impacts at a place are less directly important to risks in the UK. These systemic risks are dependent not only on scientific uncertainty, the amount of climate change, but also on how institutions and so on change. In order to estimate these systemic risks, we therefore need to blend quantitative information on physical climate change with narrative or story-based information on changes in vulnerability. So let's now turn to the UK. I'm building here on work done in a climate resilience programme project undertaken by Reading and UK CEH. The project aimed to provide policy-relevant information on future climate risks in the UK using UK CP18 projections. It's clear, of course, that different policy users have different requirements. I've boiled these down to 3 here, although there are more. Some users want high-level information to help inform overall climate policy priorities. At the most basic, is climate change a big enough problem to worry about given what else is going on? Some users want information to help inform national or local adaptation and resilience strategies. How big are the changes in risk that we need to be able to deal with? Still others want much more precise information to inform specific adaptation decisions. We focused on the first 2 groups of users and calculated a series of indicators of risk. We didn't try and estimate actual impacts, we estimate indicators of risk. I'll show here as an illustration 6 key indicators relevant to different aspects of public policy. These indicators relate to heat waves and NHS plans, to rail network disruption, to cooling energy requirements, to agriculture drought risk, to wildfire risk and to river flood risk, but there are a whole series of other indicators that are relevant. In the project, we calculated these indicators using UK CP18 projections. On the face of it, they're all indicators of climate hazard. They're directly calculated from physical aspects of weather and climate. However, we interpret these as indicators of risk because they're based on policy-relevant thresholds or values, such as the temperature thresholds that define the implementation of a heatwave plan. These policy thresholds embed current interpretations of exposure and vulnerability, so it is reasonable to think of these as indicators of risk. So here we see these indicators at the national scale. The columns show the 6 indicators and the rows are the 4 nations. The plots show the change in the indicator over the 21st century with high emissions. Basically, things get worse with all the indicators, but how much worse they get varies across the UK. For some of the indicators, things get very much worse. The national averages hide regional variability, which I haven't shown here. There are 2 general points to draw from this figure. The first is that there is some quantitative uncertainty in the estimated change in risk, as shown by the individual lines. Although the general direction of change is typically adverse, the amount of change varies considerably. You'll also notice that there are 2 colours of lines. These represent 2 different ensembles of climate models in the UK CP18 pot. The 2 can be quite different. The difference between the lines and between the 2 sets of lines reflects scientific uncertainty and largely how different climate models project changes in the details of weather regimes across the UK, particularly in changes in rainfall patterns. The second point is that the plots are based on one particular narrative, RCP 8.5, a narrative with very high emissions. This is a choice. We can choose to base our projections on this as an estimate of a worst case, but we need to be aware this is an explicit choice. However, it's a constrained choice because that is the information that we have. For practical reasons, we don't have a full range of choices. This point is illustrated further in this figure. It's based this time on the UK CP18 probabilistic projections, and this time we've plotted together the RCP 8.5 projections in the red and the lower RCP 6.0 emission stories, this time in the purple. So what should be the worst case? RCP 8.5 could be a lot worse than RCP 6, but not for all the indicators. For some, there's not much difference. But how realistic is RCP 8.5? Is it too high? How realistic is RCP 6.0? Is it too cautious for a worst case? The key conclusion from this slide is that we need to think carefully and explicitly about what we mean by worst case when estimating future climate risks. The previous slides have shown 6 indicators, all treated independently. That's okay if we're looking at direct or perhaps second order climate risks, where we can look at each sector or area of exposure separately. It's not so helpful, I think, when we're thinking about systemic risks, which can be a function of different changes across different variables in different places. It's actually very difficult to address this probabilistically. There are too many variables. I believe we have to take a more nuanced, qualitative, story-based approach. This is partly illustrated in this plot, which shows the potential change in several dimensions of climate risk in one region. It's actually the southeast of England, but that doesn't matter here. The plot highlights one particular coherent climate story represented by one climate model scenario. Different models would give different stories, but it's important to base each story on a climate model because that maintains the relationships between variables across space. Although we haven't done so yet, you can combine this quantitative information on changes in different aspects of climate with more narrative information on exposed systems and their linkages and the response to crises to produce narrative stories of the potential for systemic risk. It's a great new opportunity. I'll finish with some general conclusions. Change in climate risk is a function of change in hazard, exposure and vulnerability, and these are subject to different sorts of uncertainty. Some is scientific, but some is radical. At the global scale, I argue that the UK is most exposed to systemic risks, which will be dominated by radical uncertainty. At the national scale, risks generated within the UK, our perception of the change in risk depends on the indicator we use, and although I didn't cover this explicitly, the scale at which we assess the risks. I mentioned there was considerable variability in indicators across the English regions. However, the general direction of change is clear, even if the magnitude of change is not. This reflects not only scientific uncertainty in the change in weather patterns, but also radical uncertainty in what we choose as a worst case for planning purposes. And this has implications for how we adapt and enhance resilience. We can't know exactly what we should be planning for, so how do we incorporate this into our strategies? I think this is a really key point. I want to finish with highlighting some key evidence gaps, and plugging these gaps is an opportunity. I've divided them into scientific and methodological. The main science needs, as I see them, are in reducing uncertainty in projected changes in climate, in modelling and quantifying the linkages between risks at different scales and places, and estimating risks at different levels of warming. None of these are particularly startling, although I don't think as a scientific community we've done enough on the third point. We've become rather fixated on RCP forcings and so on, and they're increasingly diverging from policy needs. There are two main methodological gaps or opportunities to new innovative thinking. The first is on how to blend the good quantitative information we have with qualitative stories or narratives to produce good, plausible stories to inform risk assessments. I don't think we're there yet. We've got lots of the building blocks in place, but we're not thinking systematically about how to combine the different types of information. The second methodological point is a discussion around the purposes of risk assessment and resilience planning, and specifically about how we define and interpret worst case scenarios, worst cases, to inform strategies and plans. This needs to link the policy community with the science community so that we as scientists can produce information that is relevant and don't force policy communities down particular lines. There's a great opportunity for dialogue. Thank you.